With this module, we start to explore the field of chemical thermodynamics and introduce the concept of chemical potential. Chemical thermodynamics builds upon the foundation of classical thermodynamics and is characterized by the application of thermodynamic principles to chemical substances and reactions. For this, we focus on open thermodynamic systems which can exchange both matter and energy with its surroundings. Take a look at this sketch of an open system. Its state is defined by state functions describing the whole system, such as temperature, pressure, and volume. In addition, it is also characterized by the amount of substance of various species present in the system. We will denote these species with an index I. The number of particles of a certain species in the system can change. The question now is, what drives the changes in the number of particles? In general, any type of interaction between the system and its surroundings can be rationalized in thermodynamics as a certain type of work. Each type of work is characterized by specific generalized force and generalized coordinate, which form a pair of conjugate variables. This can be summarized by the fundamental equation of thermodynamics, which shows how the internal energy of a system is affected by various interactions. Earlier, when we had talked about the concept of thermodynamic equilibrium, we had outlined three different ways of how a system can interact with its surroundings: thermally, mechanically, and chemically. The mechanical interaction is represented by volume work. Here, the generalized force is pressure, and the generalized coordinate is the volume of the system. If the pressure in the system is different from the pressure in the surroundings, there is a driving force that aims to change the volume of the system. The change of volume can be represented as a move of the system along the volume coordinate. Now, what about the thermal interaction? It is clearly controlled by temperature, which is an intensive state function. Therefore, temperature is a generalized force driving thermal interactions. The generalized coordinate is not so straightforward, but we had figured out that the generalized coordinate conjugate with temperature is the extensive state function entropy. The thermal work, T times ds, represents the heat flow between the system and its surroundings due to a temperature difference. The heat flow changes the entropy of the system, which can be represented as a move of the system along the entropy coordinate. In the case of chemical interactions, the generalized coordinate is clearly the amount of substance of each species in the system, Ni. The amount of substance is an extensive state function that changes during the chemical changes. Chemical changes can be represented as movements along the amount of substance coordinates. What is missing here is the force that is conjugate with the number of particles in the system. This missing force that is conjugate with the number of particles in the system is the chemical potential. Let's introduce it formally. Consider the differential of internal energy. It can be expressed as a sum of heat flow T times ds, mechanical work minus P times dV, and the chemical work represented as the chemical potential mu I times the differential of the amount of substance dNi for all species I. Now, let's derive the definition of chemical potential mu from this equation. The chemical potential mu I for a certain species I is defined as the partial derivative of the internal energy of the system U with respect to the amount of substance of the species I, Ni, at constant entropy S, volume V, and the number of particles of all other species. This formal treatment allows us to define the chemical potential as the driving force of chemical changes. The chemical potential can be also defined using the fundamental equation of thermodynamics for Gibbs energy G. The chemical potential of a species I, represented as mu I, is the partial derivative of Gibbs energy with respect to the change in the amount of the substance of the species I at constant temperature, pressure, and the number of particles of all other types. As we mostly consider chemical changes at constant temperature and pressure, this definition is the most important for us. According to this definition, the chemical potential is equivalent to what is called the partial molar Gibbs energy of a given species in a system. In general, the chemical potential of a species I, mu I, depends on pressure and temperature. In mixtures or solutions, the chemical potential of a species I, mu I, increases when the concentration or pressure of this species increases. Importantly, the chemical potential of a species in a mixture generally depends on the amount of other species. The chemical potential of a species in a mixture is not a property of the species only, but a property of the whole mixture. However, it is not always that complicated. If the system consists of a single pure substance at constant temperature and pressure, the chemical potential of the substance is equal to its molar Gibbs energy. When discussing criteria of spontaneity and equilibrium, they remain the same whether we are dealing with open or closed systems. In an open system at constant pressure and temperature, the equilibrium state corresponds to the minimum of Gibbs energy G. Gibbs energy decreases during a spontaneous process and remains constant in equilibrium or during a reversible process. We can attribute the decrease of Gibbs energy to chemical work, which comprises the transfer of particles between the system and its surroundings. The total differential of Gibbs energy equal to the sum of chemical potentials multiplied by an infinitesimal change in the amount of substance of the corresponding species must be negative or zero for spontaneous processes and equilibrium in an open system. Note that the chemical potentials and the amount of substance for all species in the system determine not only the change but also the total value of Gibbs energy. The summation of the product of chemical potential and the amount of substance across all species gives the total Gibbs energy for an open system.